Welcome back to the deep dive. Today, we are plugging in for a pretty high voltage lesson. I mean, literally.
Literally, yes.
We're going to be exploring the science, the real mechanics of electrosurgery. It's this field that lets physicians use, controlled electricity to cut and coagulate tissue with just amazing precision.
And our guide for this, our source material, is this fantastic, really comprehensive lesson on the topic.
Right. It's a video called HCC 1472 Lesson 16A Electrosurgery Principles, and it was shared by Dr. G.S. Raju.
On his YouTube channel, Gaudamikala S. Raju, it's just a great breakdown.
It really is. And it sets up a scene that I think is perfect for us to get into. Imagine you're in an endoscopy unit, and the decision is made to cut a large pedunculated polyp.
High-stakes situation. And you can't just go in with a scalpel. This whole thing is done with heat generated by an alternating current.
And that's our mission for this deep dive. We want to really understand the core mechanics. What makes that current? What determines if it results in a clean cut or that, life-saving clotting effect coagulation?
Exactly. We need to master the circuit, the physics, and the settings that control it all. Because to control the heat, you have to first understand the machine.
Okay, so let's walk through it. The essential circuit, where does it start?
It all starts with the power source, right? The big box in the room.
The electrosurgery unit, or ESU, the generator.
Right. And its job is to take the current from the wall outlet and convert it into something totally different, a very safe, very high-frequency radio alternating current that's needed for the procedure.
But the machine itself is just the start. The actual path the electricity takes involves the patient and two other really key components.
And the first one is all about safety. It's the dispersive pad.
You sometimes hear it called the grounding pad.
Exactly. And it's this very large conductive pad. They'll place it somewhere on the patient with a lot of surface area, like the back or the loin, and it connects right back to the neutral outlet on the unit.
I always think of it as like the safety net for the whole system.
That's a perfect way to put it, because electricity is always going to look for the easiest path home.
So the pad's job is just to collect all that current after it's done its work on the polyp and guide it safely back to the machine.
And its size is the most important thing about it.
Why is that?
Because when all that current returns, it gets dispersed, spread out over that massive surface area. This drops the current density, the concentration of electricity way, way down.
Which protects the patient from getting burned where the electricity leaves their body.
Precisely. If that current was concentrated on its way out, it would cause severe injury. It's the complete opposite of what we want happening at the other end of the circuit.
At the tool that's actually doing the work, which, in our polyp removal scenario, is the snare wire.
Right, the snare. And that connects to the monopolar slot on the unit. That's our active electrode. That's where we want the current to be highly concentrated.
Okay, so let's trace the path. The generator creates the voltage, which is the force pushing the electrons.
And the current flows from the generator down the cord to the snare. It passes through that tiny concentrated area of tissue, the polyp stalk.
And then it flows through the patient's body, back to that huge, low-density dispersive pad, and finally completes the loop back at the generator.
The whole circuit is just waiting. And it's activated the second the endoscopist presses the foot pedal.
We all know the colors. Yellow for cut, blue for coagulation.
And that's the signal. The machine unleashes that high-frequency flow. And here is the absolute core principle of the whole thing.
Go on.
The heat, the thing doing the work, only happens when that flowing current meets resistance.
And the resistance in this case is the biological tissue, the cells of the polyp stalk.
Exactly. And controlling how fast and how high the temperature spikes at that tiny little point of contact, well, that's the difference between a successful procedure and a disaster.
Which brings us to the physics of it all. We have to talk about the language of control, which, believe it or not, takes us right back to high school physics.
It really does. It's a perfect, real-world application of Ohm's law.
V equals IR.
Voltage equals current times resistance. It's that simple. When that generator is firing, the voltage is the force, the current is the flow of electrons, and the resistance. Well, that's the patient's tissue.
I like to think of it like water in a pipe. The voltage is the pressure, and the resistance is like a narrow section or a partial blockage in that pipe.
Okay.
If you crank up the pressure, the voltage, you force more water, more current through that blockage. And that generates friction. It generates heat.
That is a perfect way to visualize it. When the doctor increases the voltage setting on the ESU, they are directly increasing the current flow at the tip of that snare.
And a little change in voltage makes a big difference in heat,
A
right?
huge difference. Heat generation is proportional to the square of the current. So a small bump in voltage gives you this massive jump in heat, which is exactly what you need to make a cut.
Okay, but let's flip that around. What if the tissue itself is the variable? Let's say the patient has some scar tissue, or the polyp stalk is really fibrous. The resistance is naturally much higher.
Well, that higher resistance acts like a choke point in your pipe. It's going to reduce the current flow even at the same voltage setting.
So the heat generated might not be enough to actually cut the tissue.
Exactly. And in that situation, the physician has to intentionally increase the voltage on the machine to overcome that tissue resistance and get the current flow back up to where it needs to be.
So the big takeaway here is that the ESU isn't just a simple on-off switch. The person using it is constantly dynamically manipulating voltage to manage the current flow against whatever resistance they find in the body.
All for the precise control of localized heat.
And that heat control is what lets us choose between our two main outcomes, cutting and coagulating.
It all depends on the degree and, most importantly, the speed of the heating. As that current flows through the tissue, that concentration, which we call current density, is everything.
So let's draw the line in the sand. According to Dr. Raju's material, it's actually a really clear boundary. Let's start with the blue petal, coagulation.
Coagulation is all about slow, controlled heating. The goal isn't to destroy the tissue, it's to dehydrate it.
You want the water inside the cells to slowly boil off.
Right. And that causes the proteins to denature and the tissue to kind of shrivel up and clot. But the absolute critical temperature threshold here is that the tissue has to stay less than 100 degrees Celsius.
So just below the boiling point of water, you're basically slow cooking it.
You are. And that slow cooking seals the blood vessels. It achieves hemostasis.
Okay, now compare that to the yellow petal, the pure cut effect.
This is the opposite. This requires a violent, rapid reaction. We're not slow cooking anything.
We are driving the temperature above 100 degrees Celsius, and we're doing it like instantly.
Instantly, yes. When you cross that boiling point that quickly, the water inside the cells turns to steam in a flash.
And that steam has to go somewhere.
It expands with so much force that it literally explodes the cell walls. It causes rapid vaporization. That explosive breakdown of cells is what creates the clean separation we call a cut.
So it's the difference between gently warming a pot of water and just dumping it onto a red-hot skillet.
That's a great analogy. One is a slow simmer, the other is an instant, violent flash of steam.
That clarity below 100 for coagulation, above 100 for a cut, it feels like the bedrock of all this.
It is, but the generator gives you incredible levels of fine-tuning between those two extremes, and we get that through two main controls. Peak voltage and something called the duty cycle.
Voltage, as we said, is the force. So that must determine the raw intensity of the effect.
Exactly, and the depth of the thermal injury. If you have a low voltage, the current doesn't really like to jump. It needs direct contact, and it spreads out more slowly.
Okay, so let's look at the gentlest setting. Dr. Raju's material says that we set the ESU to less than 200 peak volts. We get what's called soft coagulation. What's the clinical use for something that low intensity?
Soft coagulation is extremely superficial. Because the voltage is so low, it results in very limited heat spread. It's perfect for treating, say, minor surface bleeding or ablating the very top layer of mucosa without creating a deep, dangerous burn underneath. It's slow, it's controlled, and it's safe.
But if we need a cut, we have to boost that voltage. So anything above 200 peak volts with a continuous current flow puts us in the pure cut zone.
Right, but now let's introduce the concept that makes everything adjustable, the duty cycle.
This is the rhythm of the machine, right?
That's a perfect word for it. It's the rhythm. It defines the ratio of on-time versus off-time for the current. Instead of a continuous flow, the generator can send the current in these rapid little pulses.
And we can control the length of the pause between the pulses.
Precisely. So 100% duty cycle means the current is always on, no breaks. The tissue temperature stays high, you get a pure cut.
But if you want to introduce some of that coagulation, that clotting, you just add pauses.
You interrupt the cycle. You give the tissue a moment to cool down. It allows that heat to disperse a bit without reaching that 100-degree vaporization point.
So if a doctor wants a blend, to cut while also stopping bleeding, they might dial in, say, a 50% duty cycle.
A 50% duty cycle is a great example. It means the current is active only half the time. That brief cooling period is just enough to encourage that slow dehydration, the coagulation to happen right alongside the cut.
You're cutting and sealing at the same time.
You are. And if the situation is really tricky, maybe there's a lot of bleeding, they can push that even further.
Just an even lower duty cycle.
Right. They can drop it way down, sometimes to as little as a 6% duty cycle.
Wow, so the current is only flowing 6% of the time.
Which provides the maximum amount of cooling time. It really maximizes that coagulation effect, giving the physician total control over bleeding while they're still resecting. That manipulation of the duty cycle is really the secret sauce here.
And speaking of coagulation, we mentioned the sod version, but there are other types too, right? Based on how high that peak voltage gets.
Yes. It shows how you can get to the same result coagulation, but with different intensities. We have soft coagulation, which is low voltage, under 200 volts, very superficial.
Oh, okay.
Then you jump up significantly to forced coagulation. Now we're talking 800 to 1800 peak volts.
That's a huge jump.
It is. And that voltage is so high, the current can actually jump across a small air gap between the electrode and the tissue. It creates a spark.
And that spark delivers the heat.
It does. It allows for non-contact coagulation. The heat is delivered instantly to a slightly wider area. It gives you an intermediate speed and depth of injury, much faster than the soft version.
And then there's the most intense form, swift coagulation,
which pushes the voltage even further, from about 660 up to 2500 peak volts.
and the goal there.
Just a very fast, very deep thermal effect. You'd use it when you need immediate, deep hemostasis. The sheer force of the voltage just ensures that rapid heating and deep penetration of the energy.
So all of these machine settings, voltage, duty cycle, they're all critical, but they're not the whole story. The final piece, the one the physician controls with their hands, is current density.
Current density is the whole game. It's a simple idea. How much current is flowing divided by the surface area it's flowing through.
To get a clean cut, you need an insanely high current density.
In a tiny, tiny area. We saw it with the safety pad, right? Huge area, low density, no heat. At the snare tip, we want the exact opposite. And this is where physical technique meets physics.
How the endoscopist actually closes the snare.
Think about it. They are physically controlling the surface area of contact. If the endoscopist gets a very tight closing of the snare, cinching that wire down hard on a tiny point of tissue,
The contact area, the denominator in the equation, becomes minuscule.
and the current density just skyrockets. You get extremely high temperatures extremely quickly, and that favors the rapid vaporization we call a cut. The current has nowhere else to go.
But if they close the snare very slowly,
Then the wire stays looser for longer. There's a larger area of contact with the tissue,
so the current density stays lower for a time.
which favors that slower heating, that dehydration effect.
Yeah.
You get more coagulation before the tissue actually separates. The physician's timing and pressure on that snare is a direct microscopic adjustment of the electrical physics.
It's incredible. So you have the ESU settings, voltage and frequency. You have the size of the snare wire itself. A thinner wire means higher density.
You've also got the amount of tissue you've actually grabbed in the snare, which defines the resistance. You have the duration, how long you hold that pedal down.
And then the tissue itself. Is it scarred? Is it healthy? All of these things have to be balanced.
Exactly. So what does this all mean for you? We started this seeing a really complex procedure, but now we can see that every single choice, from the dial on the generator to the tension on the snare, is a precise, deliberate manipulation of this high-frequency circuit.
We've basically established this hard and fast temperature rule.
Hmm.
Stay below 100 Celsius for coagulation, and you have to go above 100 for a cut.
And that precision is all achieved by managing the force with the peak voltage and managing the speed and the rhythm with the duty cycle, adding in those crucial cooling pauses.
The endoscopist is like a conductor, just constantly balancing these forces to get the exact clinical result they need.
Often trying to maximize that blend effect to stop bleeding while they're still cutting. It's the ultimate example of controlled energy delivery in medicine.
Absolutely.
But here's a final thought to leave you with. We spent all this time talking about how the physician controls the settings. But think about this. How does the initial unknown resistance of the patient's own unique tissue truly dictate what the optimal starting settings should be before the physician even touches the foot pedal? The generator has to be smart enough to compensate for that initial resistance automatically, which implies a level of complexity in machine feedback loops that goes way beyond just a simple V equals IR. Something to think about.